You might think all metals are created equal shiny, hard, and useful. But there's a hidden quantum world beneath the surface that determines whether a metal conducts electricity like a superhero or blocks it like a shield. Today, we're diving into the fascinating physics that separates the conductors from the pretenders and discovering how understanding this one concept revolutionized technology, power grids, and modern civilization itself. The classical mystery: why copper works but rubber doesn't. For centuries, scientists could observe that some materials conducted electricity while others didn't, but they had no idea why. Copper wire carries power through your home, aluminum conducts heat in your phone, yet rubber keeps you safe. Classical physics, the physics of everyday objects, couldn't explain this fundamental difference. It wasn't until scientists peered into the atomic realm that the truth emerged. The answer lies in how electrons move around atoms. Enter quantum mechanics, understanding electron bands. Here's where quantum physics changes everything. In the quantum world, electrons don't orbit atoms like planets around the sun. Instead, they exist in energy bands, regions where electrons are allowed to exist. The crucial insight: in conductors like copper, the outermost electron band, called the conduction band, is either partially filled or overlaps with another band. This means electrons can move freely with minimal energy. In insulators like rubber, the conduction band is far away, separated by a huge energy gap. Electrons are stuck, unable to jump across the gap. The sea of electrons: what makes metals special? In a metal, the outermost electrons are so loosely bound that they form what physicists call a sea of electrons, a cloud of electrons that move freely throughout the material. Think of it like a crowd in a concert venue where people can move anywhere. When you apply electrical force, these electrons flow like water through a pipe. This quantum behavior is unique to metals. In non-metals, electrons are tightly bound to their atoms, trapped in place like people in assigned seats. The conductivity scale: why some metals beat others. Not all metals conduct equally. Silver is the best conductor, followed by copper, then gold and aluminum. Why the difference? It comes down to quantum mechanics again. The fewer obstacles electrons encounter as they travel through the metal's lattice, the better the conductor. In silver, the quantum structure creates almost a superhighway for electrons. In less efficient conductors, the atomic lattice scatters electrons more frequently, creating resistance. This is why power companies use copper and aluminum, the perfect balance of excellent conductivity and affordability. The temperature problem: why conductivity decreases when metals heat up. Here's a quantum surprise: as you heat a metal, its conductivity actually decreases. Why? Because heat causes atoms in the metal lattice to vibrate more vigorously. When atoms vibrate, electrons collide with them more frequently, losing their momentum. These collisions scatter the electron's path. In extreme cases, like superconductors cooled to near absolute zero, lattice vibrations nearly vanish, and electrons flow with zero resistance, a quantum phenomenon that seems almost impossible but is completely real. Semiconductors, the quantum game changers. Silicon and germanium exist in the quantum middle ground, not quite conductors, not quite insulators. They have a moderate energy band gap, meaning electrons can jump across with a little extra energy. This is where modern technology lives. By adding impurities in a controlled way, we can create transistors, diodes, and computer chips that switch electricity on and off. Without understanding the quantum band structure of semiconductors, the digital revolution would never have happened. Every smartphone, laptop, and microprocessor owes its existence to this quantum insight. From theory to revolution, how this knowledge changed the world. When physicists figured out why metals conduct electricity in the 1920s and 1930s, they unlocked the key to modern civilization. Understanding electron bands made possible power distribution networks that light up cities, electric motors that drive industry, the transistor that launched the computing age, and renewable energy technologies like solar panels. What started as abstract quantum mathematics became the foundation for an entire technological society. Your electricity, your electronics, your ability to read this all trace back to this quantum understanding. The frontier, new materials and quantum engineering. Scientists aren't done. Today, researchers are engineering entirely new materials with quantum properties never found in nature. Graphene, a single layer of carbon atoms, conducts electricity better than copper while being transparent. Topological insulators conduct electricity on their surfaces while blocking it through their interiors, a quantum weirdness with potential applications in quantum computing. Perovskites are transforming solar energy efficiency. The quantum understanding that emerged decades ago continues driving innovation. We're literally designing materials at the quantum level, controlling electron behavior to create impossible properties. The quantum physics of electron bands and conduction is one of those rare scientific breakthroughs that doesn't just explain nature, it completely transformed human civilization. From the moment we understood why certain metals conduct electricity, the modern world became possible. What aspect of quantum physics fascinates you most? Let me know in the comments below. If you enjoyed this video, smash the like button and subscribe so you never miss a video like this one.